Good day, this is Professor Will, CBMD PhD. Today is Sunday, June 21st, 2020. It is 5:27:24 a.m. Eastern Standard Time, and today is Father's Day. Today is Father's Day. Dear Dad, you've been gone a long, long time. Speaking of time, time is very special. We must make the best of our time. Time is something we cannot replace. One thing you taught me, Dad, is that to replace negativity with positive humor. We had our bad times and we had our good times. Today I remember the good times, the laughs we had together, and most of all the man you made me today. Today I'm wearing your favorite color as blue represents creativity and love. We had so much in common and together we shared our dreams. In your time of absence, I try to follow the golden role model. Deep in my heart there is a tremendous spot for you, Dad, filled with memories and love. I just want to say one last thing, Dad. You will always be remembered in my heart, and I will always love you. As the amount of computational time and memory space required increases exponentially with the number of sequences, it makes the method computationally prohibitive to use for a large dataset. For this reason, full dynamic programming is limited to small datasets of less than 10 short sequences. For the same reason, few multiple alignment programs employing this brute force approach are publicly available. A program called DCA, which uses some exhaustive components. DCA divide and conquer alignment. The breaking points are determined based on regional similarity of the sequences. If the sections are not short enough, further divisions are carried out. When the lengths of the sequences reach a predefined threshold, dynamic programming is applied for aligning each set of subsequences. The resulting short alignments are joined together head to tail to yield a multiple alignment of the entire length of all sequences. This algorithm provides an option of using a more heuristic procedure, fast DCA, to choose optimal cutting points so it can more rapidly handle a greater number of sequences. It performs global alignment and requires the input sequences to be of similar lengths and domain structure. Despite the use of heuristics, the program is still extremely computationally intensive and can handle only datasets of a very limited number of sequences. Because the use of dynamic programming is not feasible for routine multiple sequence alignment, faster and heuristic algorithms have been developed. Heuristic algorithms fall into three categories: progressive alignment type, iterative alignment type, and block-based alignment type. Each type of algorithm is described in turn. Progressive alignment depends on the stepwise assembly of multiple alignment and is heuristic in nature. It speeds up the alignment of multiple sequences through a multiple-step process. It first conducts pairwise alignments for each possible pair of sequences using the Needleman global alignment method and records these similarity scores from the pairwise comparisons. Scores can either be percent identity or similarity scores based on a particular substitution matrix. Both scores correlate with the evolutionary distances between sequences. Scores are then converted into evolutionary distances to generate a distance matrix for all the sequences involved. Simple phylogenetic analysis is then performed based on the distance matrix to group sequences based on pairwise distance score. As a result, a phylogenetic tree is generated using the neighbor joining method. The tree reflects evolutionary proximity among all sequences. It needs to be emphasized that the resulting tree is an approximate tree and does not have the rigor of a formally constructed phylogenetic tree. Nonetheless, the tree can be used as a guide for directing realignment of the sequences. For that reason, it is often referred to as a guide tree. According to the guide tree, the two most closely related sequences are first realigned using the Needleman algorithm. To align additional sequences, the two already aligned sequences are converted to a consensus sequence with a gap position fixed. The consensus is then treated as a single sequence in the subsequent step. In the next step, the next closest sequence based on the guide tree is aligned with the consensus sequence using dynamic programming. More distant sequences or sequence profiles are subsequently added one at a time in accordance with their relative positions on the guide tree. After realignment with a new sequence using dynamic programming, a new consensus is derived, which is then used for the next round of alignment. The process is repeated until all the sequences are aligned. Probably the most well-known progressive alignment program is Clustal. Some of its important features are introduced next. One of the most important features of this program is the flexibility of using substitution matrices. Clustal does not rely on a single substitution matrix. Instead, it applies different scoring matrices when aligning sequences depending on degrees of similarity. The choice of a matrix depends on the evolutionary distances measured from the guide tree. For example, for closely related sequences that are aligned in the initial steps, Clustal automatically uses the Blossom 6-2 or the PAM 120 matrix. When more divergent sequences are aligned in later steps in the progressive alignment, the Blossom 45 or PAM 250 matrices may be used instead. Another feature of Clustal is the use of adjustable gap penalties. that allow more insertions and deletions in regions that are outside the conserved domains, but fewer in conserved regions. For example, a gap near a series of hydrophobic residues carries more penalties than the one next to a series of hydrophilic or glycine residues, which are common in loop regions. In addition, gaps that are too close to one another can be penalized more than gaps occurring in isolated loci. The program also applies a weighting scheme to increase the reliability of aligning divergent sequences with less than 25% identity. This is done by downweighting redundant and closely related groups of sequences in the alignment by a certain factor. This scheme is useful in preventing similar sequences from dominating the alignment. The weight factor for each sequence is determined by its branch length on the guide tree. The branch lengths are normalized by how many times sequences share a basal branch from the root of the tree. The obtained value for each sequence is subsequently used to multiply the raw alignment scores of residues from that sequence, so to achieve the goal of decreasing the matching scores of frequent characters in the multiple alignment and thereby increasing the ones of infrequent characters. The progressive alignment method is not suitable for comparing sequences of different lengths because it is a global alignment-based method. As a result of the use of affine gap penalties, long gaps are not allowed, and in some cases this may limit the accuracy of the method. The final alignment result is also influenced by the order of sequence addition. Another major limitation is the greedy nature of the algorithm. It depends on initial pairwise alignment. Once gaps introduced in the early steps of alignment, they are fixed. Any errors made in these steps cannot be corrected. This problem of once an error, always an error can propagate throughout the entire alignment. In other words, the final alignment could be far from optimal. The problem can be more glaring when dealing with divergent sequences. To alleviate some of the limitations, a new generation of algorithms have to be developed, which specifically target some of the problems of the cluster program. T-Coffee tree-based consistency objective function for alignment evaluation performs progressive sequence alignment as in cluster. The main difference is that in processing a query, T-Coffee performs both global and local pairwise alignment for all possible pairs involved. The global pairwise alignment is performed using the cluster program. The local pairwise alignment is generated by the align program from which the top 10 scored alignments are selected. The collection of local and global sequence alignments are pooled to form a library. The consistency of alignments is evaluated for every pair of residues in the pair of sequences. A consistency score is calculated for both global and local alignments. Each pairwise alignment is further aligned with a possible third sequence. The result is used to refine the original pairwise alignment based on a consistency criteria in the process known as library extension. Based on the refined pairwise alignments, a distance matrix is built to derive a guide tree, which is then used to direct the full multiple alignment using the progressive approach. Because an optimal initial alignment is chosen from many alternative alignments, T-Coffee avoids the problem of getting stuck in the suboptimal alignment regions, which minimizes errors in the early stage of alignment assembly. Benchmark assessment has shown that T-Coffee indeed outperforms Clustal when aligning moderately divergent sequences. However, it is also slower than Clustal because of the extra computing time necessary for the calculation of consistency scores. T-Coffee provides a graphical output of the alignment results, which color boxes to display degree of agreement in the alignment library for various sequence regions. dbClustal is a Clustal-based database search algorithm for protein sequences that combines local and global alignment features. It first performs a BLAST-P search for a query sequence. The resulting sequence alignment pair above a certain threshold are analyzed to obtain anchor points, which are common conserved regions, by using a program called balance. The global alignment is subsequently generated by Clustal, which is weighed toward the anchor point. Since the anchor points are derived from local alignments, this strategy minimizes errors caused by global alignment. The resulting multiple alignment is further evaluated by NORMD, which removes unrelated or badly aligned sequences from the multiple alignment. Thus, the final alignment should be more accurate than using Clustal alone. It also allows the incorporation of very long gaps for insertions and terminal extension. The acronym POA, partial order alignments, is a progressive alignment program that does not rely on guide trees. Instead, the multiple alignment is assembled by adding sequences in the order they are given. Instead of using regular sequence consensus, a partial order graph is used to represent a growing multiple alignment, in which identical residues in a column are condensed to a knot resembling a knot on a rope, and divergent residues are allowed to remain as such, allowing the rope to bubble. The graph profile preserves all the information from the original alignment. Each time a new sequence is added, it is aligned with every sequence within the partial order graph individually using the Smith-Waterman algorithm. This allows the formation of a modified graph model, which is then used for the next cycle of pairwise alignment. By building such a graph profile, the algorithm maintains the information of the original sequence and eliminates the problem of error fixation as in the Clustal alignment. POA is local alignment based on has-been shown to produce more accurate alignments than custom. Another advantage of this algorithm is its speed. It is reported to be able to align 5,000 sequences in 4 hours using a regular PC workstation. Align is a web-based progressive alignment program. It first performs pre-processing of the input sequences by building profiles for each sequence. Profiles can be interpreted as probability description of a multiple alignment. By default, the profiles are automatically generated using PSI BLAST database searching. Each pre-processed profile is then used for multiple alignment using the progressive approach. However, this method does not use a guide tree in the successive enlargement of the alignment, but rather considers the closest neighbor to be joined to a larger alignment by comparing the profile scores. Because the profiles already incorporate information of distant relatives of each input sequence, this approach allows more accurate alignment of distantly related sequences in the original dataset. In addition, the program also has the feature to incorporate protein secondary structure information, which is derived from state-of-the-art secondary structure prediction programs such as PROF or SSPRO. Good day, this is Professor Will, CBMD PhD on infectious disease, molecular microbiology, and pathophysiology. I hope you enjoyed listening and have a great day.